Hello everyone and welcome to Keeping Tabs on Chemistry. In this video we're going to be discussing the energy of phase changes. Before we can talk about energy calculations, we first need to define what the boiling point is versus the freezing point. The liquid-gas phase change occurs at a specific temperature referred to as the boiling point. In this case, point is going to be some sort of temperature, whether it be degrees Celsius or Kelvin. Normal boiling point occurs specifically at 1 atmosphere at standard pressure. So what is the normal boiling point of water? This is the boiling point you're familiar with, 100 degrees Celsius. Now freezing point, this is the temperature at which the solid or liquid phase change occurs. So this is freezing point or melting point. That might be confusing to some of you. Why is freezing point the same as melting point? Freezing and melting actually occur at the same temperature. Whether you're freezing or melting depends on whether or not you are gaining energy or releasing it. So if you are gaining energy, you are going to be melting. If you are releasing energy, you are freezing. Normal melting from freezing point, just like normal boiling point, occurs at 1 atmosphere. So we know the normal melting point of water, 0 degrees Celsius. Now that we're familiar with boiling and freezing point, we can talk about energy calculations. We have a new term that we need to define, molar heat. The molar heat of a phase change refers to the amount of energy needed for the phase to change. The units of molar heat are kilojoules per mole or sometimes kilojoules per gram. Thinking about molar heat, the stronger the intermolecular forces holding a substance together, the more energy is needed to vaporize or melt the molecules, because to vaporize or melt, we need to break those intermolecular forces. Remember, not bonds, but the forces holding the substances close to each other. Now, the more energy needed, the higher the molar heat of the phase change. So the stronger your intermolecular forces, the higher your molar heat is going to be. And molar heat is different for every substance. So let's look at first the molar heat of vaporization, which is represented as delta H with a subscript of VAP, delta H VAP. This is the amount of heat energy needed to vaporize 1 mole of liquid at its boiling point. So we've raised the energy of our pot of water to 100 degrees Celsius. How much more energy do we need to add to actually break the intermolecular forces to go from liquid to gas? So the heat of condensation, remember condensation is the opposite process of vaporization. It is going from gas to liquid. So the heat of condensation is the opposite sign of the heat of vaporization. So delta H cond equals the negative of delta H vap. Now before you get confused, the negative sign only means that energy is released, not that there is negative energy. This is something we don't really talk about much in chemistry, is the difference between a scalar and a vector. A scalar is just a number with only a magnitude, 1, 2, 3. A vector has magnitude and direction, which we can represent as positives and negatives. So the value of molar heat is actually a vector. It tells us if we are gaining or losing that magnitude of energy. Here's kind of a comical representation of molar heat of vaporization, the amount of energy needed to vaporize 1 mole of liquid. So you can see we have a mole on the left and it is being vaporized into a gas on the right, 1 mole. Now, molar heat of fusion, or delta H fuse. This is the amount of heat energy needed to melt 1 mole of solid at its melting point. Fusion is just a more scientific word for melting. Now, the heat of solidification, which is the opposite process to melting, is the opposite sign. So delta H solid is equal to negative delta H fuse. So calculating the energy of these phase changes. To calculate that energy, we have to consider 2 things. What phase change is occurring and how much of the substance we have, either grams or moles. Now there's a general equation we can use here. The energy is equal to the molar heat of whatever phase change we're dealing with times the amount of moles or grams. Now, using moles versus grams depends on what the units of our molar heat we were given. If molar heat is given to us in kilojoules per mole, we'll multiply by moles. If it's given to us in kilojoules per gram, we'll multiply by grams. Now, the value of the energy will be in the same units as the molar heat. Notice this is usually going to be kilojoules. It doesn't have to be, it could be joules as well, but normally you'll see it in kilojoules. And the sign of the energy tells us if that amount was absorbed or released. So here's our first example. How much energy is needed to boil zero point 0.5 moles of water if the delta H of vaporization is equal to 40.7 kilojoules per mole? Well, it tells me right here that we are boiling, which means the phase change I want is vaporization. I don't have to do anything to this value. So the energy is equal to the delta H of vaporization times moles. I chose moles because the units of my delta H were in moles. Now I have both of these values, moles and delta H vap. So I'm going to input both of those, 40.7 kilojoules per mole times 0.5 moles, and I get 20.35. Now I need to remember sig figs. With multiplication, you're going by the least number of significant figures. This has 3 sig figs, this has 1, so I'm going to round this to the first sig fig. That becomes just 20, and I use units of kilojoules because my units of molar heat was in kilojoules. Now that one was pretty straightforward. Example 2 is a little more complicated. How much energy in joules is needed to melt 2.5 grams of ice if the delta H of fusion is equal to 334 joules per gram? It's talking about melting, so I need to use the delta heat of fusion. So energy is equal to delta heat of fusion times grams. I used grams because the units of my delta H are joules per gram, so I need to multiply by grams. I have delta H fuse and I have grams. So I'm going to do 334 times 2.5. That gives me 835. But I need to do sig figs. There are 3 sig figs here and 2 there, which means this will round up to 840 joules. The units are joules because my delta H of fusion was in joules. And that's my final answer. Now, example 3 is the most complicated type of question you might see in this course. It says how many grams of liquid water are obtained by releasing 40.7 kilojoules of energy from water vapor, and it gives me the molar heat of vaporization. Now, the process that's occurring here, I want to know how much liquid water I get from water vapor. To go from water vapor to liquid water is condensation. I'm given the delta H of vaporization, which means I already know I'm going to have to flip this sign. So the energy is equal to delta H of condensation. And I'll multiply by moles because this was given to me in moles. So the energy here is negative 40.7 kilojoules. Why negative? It tells me that I am releasing that energy. Releasing gets a negative sign. My molar heat of condensation is the negative from the molar heat of vaporization, so I just flip the sign. And I'm solving for moles X. Now when I divide both these, I end up getting 1. 1.00 because both of these are 3 significant figures. But the question does not ask me for moles, it asks me for grams. So how do we convert from moles to grams? We do that using molar mass. So I need to set up dimensional analysis. I've got 1 mole of water, and 1 mole is 18.02 grams. So when I solve this to 3 sig figs, I get 18 grams. That concludes our lesson on the energy of phase changes.